Hello everyone, my name is Sakari Kuikka. I'm professor in fisheries biology in Finland in the University of Helsinki. The aim of this talk is to give an overall view of the oil spill work in Finland, what we have done, and then especially I would like to success the new project between Finland, France, for example, Thailand, other EU countries and USA, because we need to establish a new project, to my mind, international project, where we learn from different case studies and take into account the risk estimates what we get from one area, that they may be relevant in other areas, to learn as effectively as possible from the knowledge available. I would like to underline especially the need to utilize the knowledge from the Gulf of Mexico case. We had discussions with the professor in statistics from the Montana University in US, and I hope that we will get connections by him to the data providers and model providers from the Gulf of Mexico case, and that these data sets are made available for the rest of the world, so that we can learn from the spills and as well know how to try to avoid the spills in the future. The title of my talk is about experiences in developing the risk analysis tools, so I will tell what we have done in the Gulf of Finland. I have had some practical experience as well in giving advice about the risks, mainly in fisheries. I'm a member of STACF, which is the Scientific, Technical and Economic Committee for Fisheries. It is the main advisory body from which EU Commission is asking for scientific advice. I'm as well the focal point member, the focal point of the International Ocean Institute in Finland, proudly new member of the organization, and I try to help to the organization to get some new items on the agenda and to try to establish some international cooperation. So the outline of the talk is that I will first speak about Bayesian inference, why we do it, why it is so important to learn from the history, and how we technically do that in Bayesian statistics. Then I will talk about the Bayesian applications in the oil spill risk analysis. I will show what kind of approaches we have done and discuss a little bit what else should and what could and especially what should be done. Then I have some concluding slides. I also criticize quite heavily the classical statistics and the current practices, which are actually not of interest to the science at all. They could be of interest to the oil companies, who actually at the moment avoid quite big part of the costs by the fact that mostly the bills they pay for the industry and so on are based only on observations, whereas we should include all the possible estimates on the industry, people and nature, and try to recover the area as well as possible and make them paying the bill. Then in the end of the talk I will success the joint research and educational project. But the starting point in Finland has been that we have several uses of the sea. Here we can see a harbor there, and there are some oil tanks. Then we have vessels which utilize the water sea area, but as well the men, in this case a fisher person, not fisherman but fisher person, who is trying to get the fish from there. She's standing on a rock which is actually part of the solid rock in Finland. This is due to the fact that we have had ice age sometimes, and the very thick layer of the ice pushed the soft material to the Estonian side, and in the end result we have the rocks in the surface and just below the surface, which is quite problematic for the vessels. We have published a couple of papers on the area. first paper, 2009, is describing actually the whole idea of why we do the modeling in the way how we do it. We create large meta-analysis models and we try to learn from different parts of the problem effectively with all best tools and then put piece by piece together a risk model which can be used for the management purposes. In 2010 we published a paper on the dynamic mapping of nature values in the Gulf of Finland. Then we published a paper on a small area but the most ecologically most sensitive area in Finland, the Hanko Peninsula, which is one area in the Gulf of Finland. That was interesting in the sense that it could show that details matter quite a bit in the risk analysis, and when you go to a large scale to the whole Gulf of Finland, you may get perhaps sometimes a wrong view of how demanding the operational decisions are in the local scale. Then we have done 2011 published paper which was 2 years result of 2 years extensive work with the published papers on the oil spills, and this was a expert-based judgment that how the combined information from the behavior of the animals and from the acute impacts of the oil on the populations, how they create the damages. Especially the behavior aspect is easily forgotten from the experiments in the laboratory, and you need to somehow take into account that the birds, for example, may be looking actually for the oily areas. Then the next paper in 2011, that is a paper where we combined the information regarding the conservation status of the populations and then vulnerability, how sensitive they are on the spills. And then on the other hand, we wanted to look at how the oil booms work in practice, so how you can safeguard some of these threatened populations, and we created an spatial index based on these values, how important the populations are from the conservation point of view, and how sensitive they are and what can be done in practice. And then finally, just a week ago we published, or actually 5 days ago, we published a paper in the Environmental Science and Technology, which was about the optimal location of the oil combating vessels in Finland. And this is the work what we would like to continue and focus then during the next years on some other areas just to learn well, and Thailand would be an excellent place to do it because Thailand has good scientists in statistics, and then on the other hand the oil spills matter much for this area. But first I will start by just considering what is the risk and why we do need Bayesian inference. Risk is something what is in our minds, especially in a case that it has not realized, so everyone has a slightly different view about the risks and uncertainties and what kind of risks we are willing to take. In the upper photo there is a person skating on the ice, and she seems to trust on the person behind the camera and skating happily and enjoying the environment. That is based on the fact that somebody knows that the ice is going to be strong enough and you can skate there, at least close enough to the other people. That was the feeling of the person. She considered that okay, this good experience is more important and provides more happiness than the slightly small risk to have a problem with the ice. So it made sense to take the risk. But this depends on quite much that how much you know. That is base of the feeling, and this describing how much you know is also an important part of the Bayesian inference, and that's why we do this models with the Bayesian methods. On the other hand, in the lower part, in the lower figure, there is a young boy, who clearly enjoys taking the small risk by sitting in front of the vessel, enjoying the fact that he can control the situation. He wouldn't be there likely if there would not be a skipper in the vessel, and he can trust that nothing serious happens, and if something happens, somebody will help. And these kind of elements, that can you trust someone, can you trust the advisor, they have an impact on how we understand the risks. And all these kind of elements are involved once we try to communicate the risk to those people who are supposed to react to the information what we provide by scientific tools. First, I would then say a couple of words as well about the need, that because we need to avoid the disasters, we need to avoid the unseen things. So there is no data, and we don't want to get the data. We don't want to get the data which describes all those damages what can happen in the Gulf of Finland. So I feel sympathy for the man in the middle who actually, to my mind, behaves like someone who is doing classical statistics, that tries to forget that there are actually much bigger uncertainties in the knowledge what we pretend. But somebody needs to do something, and somebody needs to manage, and that is the point. In the next slide, I have a picture of the different sources of uncertainty. There's the natural variability in the climate, for example, and then we have uncertainties related to the model selection. There could be different ways to describe the impacts of the oil. We have uncertainty in the parameters. Different sets, combinations of parameters can describe the data almost as well. So data alone cannot say what kind of parameter combinations are justified from the scientific point of view. And then we have implementation uncertainties, that if you give a recommendation, so how many of the vessels really behave in the way how we wish. Usually this latest part of the uncertainties is almost totally forgotten. And the lower figure is an illustration how this kind of selections, which are often made by the scientist, one scientist or a couple of scientists, how they actually impact on the uncertainty estimates what we get in the end. And you need to be careful to describe all the possible ways to all the different model structures, which means the causal nets which are perhaps behind the damages. Here I describe the relationship of the data and our understand the real number of the fish in the sea. In the upper figure there is the way how classical statistics is thinking about it. So it thinks that for each amount of fish in the sea there could be different kind of observations, which is true. But on the other hand, once you go out to the sea and do your acoustics, for example, you get a certain number of fish to your estimates of certain number of fish in the sea to your computer. And that's a fixed number in your computer. So after that, a Bayesian modeler starts to think that, okay, this is a fixed number, and it can actually come from several sizes of the stocks. So there is an probability distribution describing that, given my data, what kind of sizes of populations there could have been in the sea. And this is the knowledge what we provide to the decision makers. This is an illustration of the fact that then in the Bayesian inference you have the prior first by blue here. Then you have the likelihood what you learn from the data, which is in this case suggesting that there is more fish in the sea than what we imagined. And then the posterior, it's a combination. It is a view between these two values, because you compromise between what you thought in advance and what you learned from the data. So you don't trust on one of these only, but it's a compromise. This mimics, to my mind, the human thinking very well. In this figure, we describe the fact that you can model, for example, one year class in the population first by models in the upper figure. Then you get some environmental knowledge year after. you learn a little bit more, you can predict more precisely. Then with the survey data, once the vessels are out, you get more information about the recruitment that year. When they are 2-year-old fish, you can get good acoustic estimates. And then finally with the catch data, once you start to see that how many fishermen are able to take from that year class, you will learn more. And by combining all this information, in the end you are more certain about the size of the stock than you can be with one model only, or one data set only. And this is true as well if we think that there will be different papers published about their sensitivity on oil and so on. We need to utilize the information in the papers first and do meta-analysis to be as certain as possible with the published papers, and then look at the data that can we learn something more. Now I will go to the oil spill risk analysis, and this is also a story whether you want to be the master of the lighthouse or the commander of the oil combating fleet. This is the basis of the risk. It is in Finnish, but it describes that how much over the years the total amount of oil exported through the Gulf of Finland has increased. And we see that the new harbor, Primorsk, which is an important harbor in Russia, it's providing quite big proportion of the total oil in the Gulf of Finland, and it seems to be that it is a peaceful way for Russia to provide the oil to the international markets. International markets are asking for that, so it is a joint interest for the humans to have this, but we need to control the risk somehow. This is a figure from a very recent 5 days old paper in Environmental Science and Technology, written by Annukka Lehikoinen and co-authors, and it describes how we did the modeling for the optimal location of the oil combating vessels in the different parts of the coast. And it describes as well the pathways through the Gulf of Finland which tankers are using, and we have estimated the probabilities for the spills or the accidents in the different areas. And then in the next slide we demonstrate how we use the oil spill models to describe the spread of the oil running through the observed weather data, and in this way trying to simulate precisely what kind of weather combinations there has been in the history, and then looking where the oil likely goes from different accident areas. Models are behind these risk models to look at how likely it is that the population suffers. But basically we are interested about the fact that we are modeling things that cannot be seen. So in addition to the data what can be observed, we must be able to somehow estimate what else happens. And that estimate cannot be based on, it's not right to ask, let's say in the court, that you need to have data to show something. If the experts agree and the existing knowledge agrees that there are damages which cannot be measured, they are still damages which need to be covered by the oil companies. So we should be somehow aware of this, and we should be able to convince people that there are damages what can never be observed, and especially if a damage happens quickly, so there is no time to or no chance to get the survey vessels there and do all the studies. So we have to trust on the knowledge what we accumulate from the previous accidents. And I would like to underline that we need field surveys, we need experts, we need publications, we need laboratory experiments. We need to learn especially from the close-by situations, like is the case in the airplane activities. On the airports, if there is a close-by accident, it is studied very well, and the lesson to learn is taken from that knowledge. But how do we do it? It's not easy. It's theoretically demanding job to transfer the knowledge from the laboratory and theoretical models to model what kind of uncertainties there are once we need to expand this knowledge to the nature. And we as a society, we need to trust on the science here, and let's say that in the nuclear power risk analysis we are able to utilize this and kind of theoretical knowledge, and we should be able to use the same thinking in the oil spills as well. I am asking that why don't we just learn from the models and act? That why the EU legislation packages carry the names of the oil spill disasters? Why we can't do good legislation without this learning from the cases? That's my serious question. But we have provided some methodology by which you can model these kind of things, and they are Bayesian networks. There is an example on the right where we have modeled certain sub-task of the oil spills. This is related to the paper in Lehikoinen et al., which was published 5 days ago, and it is a submodel from that paper. But you need to combine the expert knowledge, and you need to identify the probabilistic chains in the system by which, if you manipulate that chain from the first variable, you can manage with the decision, and then it has a strong impact on your interest in the end through the noisy chain. So that's a valuable control, and that should be utilized. So there is a need to as well to look at the different views. It's obvious that the different stakeholders, different interest groups in the society have different aims, and these alternative aims should be part of the inference what we are doing. You should test what they mean in the sense of decision making, and in the end you may agree to have certain utility functions, but you may want to screen out what the extremes mean. I have an example here from a conditional dependency between the spill size and the length of the old coastline, how much coastline we could lose in a case of a spill, and depending on different sizes of the spill. So this is a table which describes that the probability for practically zero spills in a year is lowest. 87% of the probability is there. Then some probability for spill between 500 and 1000, and a little bit more likely that if probability for spill between 1000 and 5000. So in this case we believe that if there is a spill, it is always a little bit bigger. So this is not a standard probability distribution. You should actually model separately the probability for a spill, which gives the first class estimate, and then after that you look at that, okay, if a spill happens, how big it can be. So it's a combined probability distribution. And in the end we don't believe too much on the biggest scale accidents in this case, but this is the prior, what kind of probability there is at the moment for a spill, and graphically it looks like that. And then we have the conditional probability for the oiled coastline, öljyntynyt rantaviiva in Finnish, sorry about that sentence there, but this shows conditionally that if there is a certain size of the spill from 0 to 500, how much coastline is oiled, and then you model these dependencies, conditional dependencies, so that you look for each size of the spill how much coastline we lose, how much is oiled. And this shows now the probabilistic dependency between these two variables, and this is modeled by the models which describe how oil behaves in the surface. And then you can modify it as well to be a decision model, that you add an action there, and then you add some kind of utility, in this case loss, that how much money you lose or how much willingness to pay among the taxpayers if you have a spill. The willingness to pay is likely a better one than the realized cost, because in the case of realized cost, you are only paying for those money which was really lost, which was used for the combating activities or so, but you don't include the estimates for the rest of the nature damages. So it is always easily an underestimate what for example, the oil companies need to pay. Then we can model these together, and in this case we describe with a simple example how total nitrogen, how chlorophyll A is depending on this, and then in the end how the Secchi depth, how clear the water is dependent on the chlorophyll A. And in this case this is directly learned, these conditional probabilities from the data. There is no probabilistic model whatsoever, just the data, which means that in the probability distributions the sampling error is included, so it may give a little bit too noisy view, but on the other hand this data is already filtered and some kind of aerial means are used, so it's not really the very original noisy data in that sense, but it's quite philosophical question that what is the correct way to do it, because on the other hand when people happen to go to the sea and see it in which condition it is at that moment, so it is this kind of random process as well. And then there is a figure which describes that how we model the long-term and short-term and long-term impacts on some biological groups in the Gulf of Finland. The lower part of the model is based on the expert judgments, because it includes as well both the ecotoxicological impact on the populations, and then as well the behavior element of the populations, how likely it is that certain groups of birds accumulate to the oil areas and so on. So it is a relatively complicated case, and let's say if in a case that you would describe this all with dynamic models, behavioral models, it would be really an expensive study to do. In this case expert made it based on 2 years work, and it was published then to serve as a prior for the other case studies in the world. This is what we learned from the case of Gulf of Finland. Then in the upper part there are parts which are estimated with physical or theoretical models describing the evaporation, wave height and oil type dependencies, and then some agent model which is actually coming from the latest paper, Bayesian and al, and then some estimates are based only on the data, on the frequencies of the data. It depends on what kind of question you have, that do you have data available, is the theoretical model so good that you can work with that, how you then take into account the other information than the theory and so on. But these are big questions for the modeling in general, and you need to be careful with those. In ProPub's project we looked at the cost benefit issues in the oil combating oil management strategy, whether it makes sense to invest on actions which prevent the spills, or actions which are used then after the spill, oil combating, which is for example the investment on the new vessels that collect the oil from the surface. We just in Finland we bought the 18th new oil combating vessel. It was something like 45 million euros. And it is certainly nice to be a commander for such a fleet, but the question we wanted to make for the society in general is that if the government uses money, so should it use it rather on the ministry which is responsible for preventing the spills, or should it use it for purposes after the spill? Then you have lost already something. If one spill takes place it's very costly, and the damages what are not paid by anyone are high. So just by saving one accident, you actually, by preventing one accident, you save quite a lot of money. And this was the question. So this upper part of the model is coming from the previous figures what I showed. There are the same elements, but what we have done is that once we have done that part of the model, we added now the economics to that model. And there was one person who was working with the economic issues for about half a year. And this describes the best knowledge what we could obtain in that time period, which I think it is actually quite good quality of the knowledge, and that is used to describe what kind of operational costs can happen. The way how we evaluate the such a Gulf of Finland where there is no oil is based on the willingness to pay estimates, which are based on the questionnaires made to people in Finland. And that is one way to evaluate that part of the nature which is not covered by any insurance companies or so if a spill takes place. And then we calculated that what are then the costs related to if a spill happens. Behind all this is the very essential question, how likely it is that an accident happens. What is the probability for the accident? And that's not an easy question to answer. Then I have some concluding slides. Publication practices first. We should actually give up from the fact that what we do with the classical statistics is that we somehow pretend that the one who is going to use our information is interested only about the data, the information content of the data set we are analyzing. Certainly we should utilize the other available knowledge to make the final information user to be more satisfied on the fact that now science has looked at the other sources of the information as well. And we actually lose quite a lot of information if we don't build on the previous papers at all. In this case, to my mind, it's really crucial to get out as much information as possible from the Gulf of Mexico case. It was a public disaster, and that knowledge needs to be available for the other parts of the society to be able to discuss in a relevant way with scientifically justified arguments that how much we need to invest to try to avoid such spills. I understand absolutely and totally that British Petroleum, for example, has an interest not to make it public because of the bias provided by the classical statistics. You basically always underestimate the impacts. I think the classical statistic is doing it all wrong. It provides a systematically biased view. If you are able to publish only papers where your p-values happen to be low enough so that it's very unlikely that you have seen the data given the hypothesis. So they are extremes. It's not the descriptions what happens usually in the nature, if that is used as a criteria. So we get a systematically wrong view about what is going on in the nature if we do that. It should be illegal to publish papers which include p-values. But we do have some hope if we learn between areas, species, environments, disciplines and cultures. And this learning from Gulf of Finland and looking how it could be used here, learning from Gulf of Mexico, how it could be used here in Thailand, and then what we learn here to reflect back to Gulf of Finland. That's what we need to do, and learn the methodology as well. So the work should look like this, that once you have done the first paper ever on some topic, you publish it, and your posterior is then the prior for the next study, which decides by what you have learned how much it makes sense to invest on new research, and then provides again a posterior, which is combinations of your first knowledge and what was learned in addition. And this is the way how the science should be rolling on. It's not obvious that how you really utilize the prior from previous studies in all cases, but there are elements which are certainly better to utilize than not to utilize. It's an endless discussion that how the prior should be derived, but it's certainly better to use them than to pretend that there is nothing useful in the previous papers. It's wrong for your colleagues in the rest of the world as well. So, to my mind, we badly need extensive risk analysis to show what we can lose. We have to make them aware what can be lost. And then the final slide is about the possible project, what I think we should aim for. We should have a joint project together with Thailand, US and Finland. We should have several scientists working in these areas. We should utilize the knowledge for this here, and we should educate the people. We need educated people to do this kind of risk analysis and to expand that knowledge. I will contact the foreign ministry in Finland about this. Likely I'm going to use these slides there as well. But in the short term, to get this system rolling, to get something to be done and some results to be shown to justify this project, I think we need to take the next step relatively quickly. And I have an idea to get a PhD student from Finland to work with this as the last paper in her thesis. And I have discussed this already today actually with 2 universities and as well with the Professor Borkowski from the Montana University, who is professor in statistics, and he seemed to be interested about the issue and especially about how you do the optimal survey, given the fact that those estimates which are for areas which you can help with the booms are more important than estimates for the areas where you cannot do anything. So only the knowledge which helps you to do some relevant things is valuable, or it is more valuable than estimates for issues for which you cannot do anything. I aim to have a scientist visiting from Finland to Thailand next year, and then we will have a workshop organizing a workshop together with the International Oceans Institute. Sersak Irapat is the head of the institute, and we aim to have a workshop in September in Thailand. And actually I have obtained quite a lot of interest during this trip, and I would be extremely happy to get those students. And there was an interest, and people seem to be very well educated in Thailand to learn and adapt this kind of new methods. Thank you everyone, and I sincerely hope that we will see you all in the future. Thank you. So after this in the end I would like to demonstrate a little bit the risk attitude and how much the role of knowledge matters in the case that how we understand the risk, and in this case in the project I succeeded, it is about improving this knowledge before anything happens, so that we learn from the history what we have had. This is the starting point. Would you like to go skating there or not? Who in the audience, hands up, who would like to go skating there? There is a sign that somebody has been there already, but let's see what happens. How much you learn from seeing what happens. There is now a young lady skating. She enjoys, clearly. And the man following her, seems to enjoy as well. It's beautiful. This is the Baltic Sea. Ice covered in the wintertime. So You feel more safety after observing the fact that there was no risk and people in the video enjoyed it. You trust on that observation. That indicates that there is no risk, or does it actually? Let's look again. You get now a prior from the fact that it's enjoyable, it's not risky. But what are you thinking after the next video? Do you update your prior view about risk? You see now that there is something wrong with the ice and there is a man there. Is he too heavy? He has been able to break down the ice, or what has happened? What is logical reaction? He comes, he's a big man. What may happen now? Oops. Nothing happened. So the risk was not realized in this case. And they seem to be happy both. So that was my view about the risk. Your view may differ. It depends on what you know. I had an experience which helped me to do this. My daughter had no similar experience, but she was able to learn. She trusted the scientist, the father, in this case. I think the laugh in the end indicates that risks were clearly under the control. You enjoyed it, and it was quite fun, a little bit exciting, but fun. So thank you for this moment. In the end, I would like to show you my photo from the Gaudí's house in Barcelona. It is the house where the sea lives inside of the house, and this is one of the views. It looks pretty house, and I hope that our oceans will look as pretty in the future. Thank you. Finally, my dear listeners, I would like to acknowledge the Baltic Sea and the Fisheries and Environmental Group in the University of Helsinki for the good motivation. The photo is already about 15 years ago, but I still remember these days very well, Antti and Maria. Thanks for that.